Hey, it's all good? Yeah, I think it's all good now. Thank you. Well, thanks again. And Zubair, thank you for the kind invitation to come and speak to you here. Zubair asked me to focus my presentation on technologies, uh, all my research about offsite construction and modular, but he asked me to look at the aspect of from lab to commercialization. So I will share with you a couple of projects which I'm working on. I'll start with the precast or concrete. So I start to look at concrete the way we treat it, and we treat it as a cheap product, and we can put it anywhere we want it. But if I look at the steel, I-beam is really an efficient design. So maybe I'll use this mic. So the I-beam is a very efficient design, and the steel is put where we need it to work, whether deflection, shear, or any of the other capacities. I look at the wood, lightweight wood structure. It's another efficient design. We don't put wood everywhere. We put it exactly where we need it. If we look at the industry, also change the I-beam. So this is the University of Nebraska beam structure. So the rebar is where is needed. I'll see if I can point with my mouse. And it's not really everywhere, but the concrete is really hugging the rebar, and that's what it needed. The concrete, the rebar must have what they call it coverage. Then if you look at the concept of double T, same thing. The concrete is where the rebar is working, and they work together as one member. The double T also provide opportunities to use the infrastructure, which is mechanical system and others, under the between the ribs. When it comes to slab, we designed the slab for both members, whether reinforcement and concrete to work together. And then for simplicity, we put a platform, a formwork, and then we pour concrete everywhere. Not necessarily that all this concrete is really working at the same time. So most of that concrete could be probably just for simplicity is being put together. So the question I raise, why we don't learn from the steel structure, the timber structure, and use as much concrete as needed only without going an extra level of concrete. We all know formwork is expensive, and it's really costs a lot of money, cause a lot of waste. Most of the formwork would have wood elements, and most of the time we may not really use all that at the same time. Some studies demonstrated that the cost of formwork could contribute to about 40% of the cost of the concrete when you have a concrete structure in a high-rise building. The challenge of the current system is also it's nice and smooth surface, but the floor has multifunction. One, to hold us on top of it, but it also to carry the infrastructure under that, which is the mechanical systems and piping and all that. So when you have that smooth surface, what you can see here, this is from my lab at the university. All this infrastructure has to be suspended from that ceiling. So the industry reacted and say, well, okay, we can reduce the concrete by using what they call the waffle system, which is similar to Belgian waffle, which you can probably see it in. So that you reduce the concrete dramatically, really. It has a little bit of challenge if applying it and cost of making the foam to make it work. Yes, you reduce the concrete, but to make it work is really costly in terms of labor and on-site work. The waffle system, I took these pictures from a project in Brazil. So what you can see here in the vicinity, these are bathrooms. We build modular bathrooms and we bring them in. And it was an opportunity for me to take this picture to share with you. Beneath that waffle system, we have to suspend all mechanical system again. So it did help some, but other consequences did not solve all the problems. Precast is not new. It probably has more than 90 years in the making in the construction industry. We have what they call a sandwich panel, concrete, insulation, another layer of concrete. There is way more concrete in that slab, in that panel than needed. To react to that, make it efficient, the industry start automating the process. And to open a factory called precast, you may need to spend in excess of $20 to $30 million, that US dollars. And I have other numbers, which is much higher than that, because it really had to be automated in a way to gain some efficiency in the process. So the question I raise, how I can learn from the steel, the wood, and make the precast concrete to be more efficient. And that's what the concept I came up with, having a structure look like wood, but it's all monolithic concrete. So this is the precast factory, which is from the lab, what you call it, to commercialization. It's mimic the wood construction. You have sheathing from outside and stud, and between the stud, you can put your infrastructure, which could be mechanical system, electrical, and the rest of it. So I have to bring efficiency, and that was the biggest challenge I had. The first layer of efficiency is the concrete itself. I start using high slump, 180, 200, and nothing worked. It took a long time to put it between the ribs I have. So I start using what they call it SCC, self-leveling concrete. There is a premium we pay for that, but again, it gives you higher quality product, but again, gave me also the efficiency. I use a styrofoam system as a forming system. And the styrofoam layer, which is 1 inch, I leave, that goes with the panel and provide an opportunity for either insulation or acoustic layer in the system. In the factory, we manage also to add multiple layers. So I can finish the product from outside to eliminate the need for cladding or stucco or any other member. So it's an efficient system. And you put it in a way that the way it is light, I can really have a full span. The challenge was, okay, we all make walls or precast, but floors, we have only a hollow core system, which is not really the best system you can have. So I designed the same system with a little bit deeper joist, so I can have the same system for floors and for walls. You ship it in the trucks, and then once in the truck, you can transport it to anywhere. Most of my projects are between 1,000, 1,500 kilometers away from the factory. So this, and then the house will be built. This shows the entire system, a floor and a wall together. And between the floor, if you can see on the right-hand side picture, there is room for mechanical systems all wrapped in. So eliminate the need of guesswork, and your mechanical system is as per design, as the way it is designed by the mechanical engineers. Give you the opportunity in the factory. You can see your backing for closets or kitchen cabinets and all that. And you erect it in a very short period of time on site. The project you see in the front of you, I think, was done in about a week and a half, 2 weeks time. This project was done. So the rest, the owners will have to go to finish from inside. So these are the panels. I had to design a special lifting system, which you see the spreader bar, to allow me efficiency on site as well. So you cannot really have one efficiency and then all of a sudden somewhere else you lose the efficiency. It has to be encompasses all the areas of efficiencies. And we start raise the bar for quality. The customer, they are not kings, but their homes is their castle. So you need really to give them all what you can to give them the best quality. And that could be done in a factory at no really additional expense. You can see here the finished product, reduce the need for any other additional members, but again, give the client the type of surface they need. So this is a precast factory, which I opened in my city, and we've been building for residential construction primarily and some commercial projects. The other part of the research, the sound is not coming here. Some of you may have heard about this project. So this is volumetric modular system. One of the schools wanted to build student dormitories, for example. And then the question, can you build 5 buildings in a single summer, which is the short summer in the US between mid-May until end of August. So these models were built in a factory, volumetric, and put on site in a very fast. So I built the 5 buildings, 3-story each, in 10 days for this particular university. The modules were fabricated, cladded with brick from outside was the biggest challenge. And everybody around, they will question, can you really ship 69 miles away from the factory. And the trades, they told me, yes, we can. So they come up with multiple solutions for us. So these models were fabricated, shipped to the site, and put together every single day, or day and a half, we will do a full building of this size. The challenge I faced is on-site trades. Because they're used to working in a way that they improvise and they do things the way they like to do. So they run from one project to another, multitasking. And I try to push them hard to make sure that everybody, I put the trades on, give them code, who need to be when and where, and their work is scheduled. If you look at the schedule here, is per minutes. So there are minutes to do things rather than hours or days. And that was the first challenge I faced, and took a while for me to get the industry accepting this type of concept. So the biggest challenge I also discovered in the factory. So we apply the principles of lean and other principles to make efficiency in place. But when I look at the factories in North America specifically, those who are using wood construction, the lean principles, I listed some of them here, are all violated in a way. So at this particular location, what you see here, these are people who are making a rim board for a wall, for a floor, and the floors are 15, 20 meters long. They have to make them out of pieces of wood, which is 2.5 or 3 meters long, and then they move it back and forth. So you can see the people, and then you're bringing the joist, and the joist is located in one place, and they have to move back and forth. And I counted about 1,800 steps to bring the joist from where it's located to that place. And then all of a sudden somebody will come in with a nail gun and apply 5 or 6 nails per joist from each side, and then move back on and forth. So if you look at, like, it's a chaos in a way, but people working in it. And I all usually make a joke here that they don't need to spend money on membership for gym, because all what you do every day is a hard work and gym-related activities. Very few changes we propose for each one of these activities. I'll show you some examples. Move that gas plate to where it's needed. And all of a sudden, I was told by this factory, they saved about 4,200 hours a year, because they make about 600 floors a year. So the saving became evident and very simple, little automation. If you look at the system, only I moved that gas plate to where it's needed. Instead of moving back and forth, you can use the gravity to your advantage and bring the material next to the people. So this way the people they don't have to walk around and back and forth to bring the material. You can also rebuild some of those outside the production line. The production line or the station is the jewel. That's where you make money. You make money as a factory when the wall is out of that station. So that's basically, you can do everything possible outside of that station and make the station the most efficient. And that's what we need to focus on. The other things I noticed that people like to run back and forth. The philosophy in the factory, fix the people, fix the tools, and then bring the product to the people where they need it, where they are, and all the tools should be available for them. If you apply this philosophy, you can have what I call it predictability. And the most common elements on the factories, which they're told, yeah, we're doing X amount of walls per day, or X amount of floors, or X amount of modules, but there is no one will tell you with certainty how long does it take each single activity in a factory. But when you fix the people, and then the other notice I did the other aspects I noticed is they build in the factory the way we build on site. So if the wall made of 40 or 50 walls, they will build each wall separately and then put them together afterwards. We encourage the factories to build all interior walls together because they have the same size, and all exterior walls together. So this way we can reduce the number of walls, and you can gain substantial amount of efficiency by just doing that. The other challenge I discovered also, I was a victim of that. This is one of the projects I did myself. So we put what they call a tag time lean concept, and each station will have X amount of work, and will the people work in and move in. But when I made the animations with the students, we discovered that, okay, well, wait a minute, these people have to go through one single door, in and out. And that provided a challenge, and I could not really make with certainty the amount of time it takes to do a certain amount of work. So we have to move away from that and then make sure that the elements, if I can put it in a 2D rather than 3D, was a little bit of challenge to be accepted, but eventually the industry found a way that, so the other discovery also, lots of manual work in the factory. We call them self-manufacturer, but they are really stick builders or conventional under the roof. So applying a machine that will mimic the human behavior, the best is really robotic arm, multiple degrees of freedom. But robotics still in construction is not the best thing to talk about because we need another 5 or 10 years. You will see every factory will have robotic arms. But today, the fear of robotics is much higher than the being able to make it acceptable. So I'm doing 1D at a time and mimic the operations in a way that I can apply the second degree or third degree when I need it. So things move in one direction. So this is the machines which I proposed and built to mimic the operations of the human. So there is a machine on steel and machine with for wood. Let me see if the only challenge I can't advance it seems to be the file. So the other one, which is light gauge steel. So wood framing machine exists already in the market, but light gauge this is one of a kind to put steel walls, light gauge steel for interior walls, specifically in commercial buildings or office buildings. The speed this machine can provide the walls cannot really be done the same way if you just manual operations on site. So there is a bridge. I put multiple tools, and these tools can operate almost you're having multiple people working in the same station. So this is the final products and very simple machine. So I'll show you some if it's in action. You can see the human here is fixed. The machines is fixed. The tools are fixed. And all the elements are coming. And this human is moving within a very small circle. So then I can predict the amount of time it takes to produce or to make a wall based on these automation, if I call it semi-automation, because there is a human involvement. So in this particular machine, I have probably 50-50 between human and machine. Other machines, you will have more than 80% in the machine and 20% human. So it depends what the operations. If you look at the window here, we have a budget of 6 minutes per window because now I'm doing a 2D rather than 3D. So that's really give me a predictability. If the size of the window is high, you can see there is a suction system I can use to apply. 2 people can do any window in about 6 minutes. The biggest challenge I also discover is the commitment to drafting and design. We use Revit, for example, which is the most predominant product we have in North America. And it takes a long time really to convert the wall or the file into panels that I can use or fabricate. All I needed is to push a button, I get all the walls. So the factory I showed you earlier, the precast, to get the shop drawings, I kept adding people. We have 7 people. It takes 7 to 8 weeks. So I spent a lot of energy with the students and convert that into software. And now with the programmers I have today, it takes 10 minutes, all that. So I converted from 7 to 8 weeks to 10 minutes. My production of the wall of the system, which I needed the drafting and design for the system. Yeah, the next generation will be digitalizations and having digital transformation of information. It is coming, and probably will be the most efficient way to transfer information rather than removing the guesswork from the system. The future is for robotics, but I'm not really yet committed to that given the resistance from the industry. And with this, I conclude my presentation. I'm showing you here a demo of the machine, which is I'm commercializing this summer. So from lab to commercialization is the title. So the first commercialization was the precast, and this is the machine which is I'm commercializing hopefully this summer. And with this, I conclude my presentation. And I know we're behind schedule. We started a little bit late. And thank you for coming early and listening to my presentation.